Okay, we're on example 16.2. So this is showing you a picture of an electroscope, which I have some of, I have some of these in the classroom. I don't know if you've ever seen them before. They're in a cabinet, but they have these gold foil leaves, and what happens is you can cause them to, the charges to kind of flow through this bulb here that's metal, and if you get the same type charges on these leaves, they will repel. So it's saying that the electroscope is charged negatively, and so the foil leaves are apart, and it's saying what happens if you do the following things. So the first one, if you touch the metal bulb with your hand, what happens to it? Well, you are in some way grounded, because you're either standing on the ground or you're standing or sitting on something that is touching the ground, and so the electrons are actually going to flow through you and you're going to ground it. Okay? So that's basically the first one. The second one, you bring a glass rod that's been rubbed with silk near the bulb, and it does tell you that a glass rod is positively charged. So what happens to that? So I'm just going to put, I guess I should have said on this one that you ground it. So on the second one, what happens is when the charged rod, the glass rod, is brought near the electroscope, the opposite charge, so those electrons then will move to either end. So because the rod itself is positively charged, those electrons will move to the top, and then the bottom will then be left with positively charges, which should still cause those leaves to repel. Okay, the third question, I forget what it says. It says that the glass rod actually touches the metal bulb. So what happens there? So whenever that happens, so when the rod, I guess I should be more specific, the glass rod touches, because it's positively charged, this is positively charged, negative charges or electrons flow into the rod. Kind of like what they did with that metal sphere whenever the glass rod touched it, and it actually causes the rod to be neutralized. And then that's causing the electroscope then, I think there's a lot of commas in this, it's okay, I'm not an English teacher, causing the electroscope to have an overall positive charge, which still means that I wish there was a picture of this, which causes the leaves to be apart still. So that was kind of a lot, and my handwriting is atrocious, but it's kind of hard to write with this pen. Okay, so next section, Coulomb's law. So Coulomb, that's what charges are measured in, are coulombs. gives the electric force acting between 2-point charges. So, you know how I don't know if you remember this was a long time ago because it was last semester, but we had Newton's law of gravitation. This law is very similar to that. Hopefully the equation looks similar. It's a different equation, but it looks a lot like the same. So what this deals with is a point charge is a point-like object with a non-zero electric charge. So it's going to have some electric charge. The electric force is inverse square law force. So what's saying is, if we were looking at universal law of gravitation, we had like this big G times mass 1, mass 2 over distance squared or radius squared. So for this one, for coulombs, we have force, this is like your electrostatic force though, is equal to K, which is Coulomb's constant, which I'll give you in a minute, times Q1, Q2 over R squared. And K is equal to 8.99 times 10 to the 9th Newton meter squared per Coulomb squared. And then, I don't know why they always do this, because to me this is kind of confusing, but they give you this permittivity constant. I'm going to go ahead and give it to you because you do end up needing to use it later on in other chapters. It's kind of this weird symbol, an epsilon, which is 1 over 4 pi k. So 1 over 4 pi times Coulomb's constant, which is actually equal to 8.85 times 10 to the negative 12th Coulomb squared per Newton meter squared. So if you were going to rewrite this one using the permittivity constant instead of Coulomb's constant, which, like I said, you do end up kind of using later on, but not yet. So what happens is you end up with Q1 times Q2 over R squared times 4 pi, and then you have this epsilon. So kind of weird, but it all works out the same. Okay, so let's just look at these figures for a minute. First, what I want to point out is see how you have two different charges. You've got a positive and a negative, so they're obviously being attracted, which is what they're showing you. Showing you that the force is being attracted. Now, this always gets people because people think force 12 and force 21. I don't know why they do that necessarily, but this is really like a comma kind of here. It's like force of charge 1 to charge 2, and then force of charge 2 because of 1. So that is what that means. And then it's showing two positives and two negatives repelling each other. Okay, so we've got this example 16.3. And this is one that I feel like is pretty intense, okay? So I'm probably just going to make this its own video because I don't know how long I've been talking, but probably a little while. And then we can just devote a whole video to this sucker. So I will see you in the next video.